Started talking about some specialized algorithms to compute power spectra. You would think maybe, well, I mean, we talked all this, we did all this work on talking about the Fourier transform, and then we talked about computing power spectra. We actually looked at applications of two-dimensional power spectra in imaging. And so why is there a need for additional types of algorithms? And the reason is that on one occasion, and that's the first algorithm I want to talk about, is that sometimes you cannot get evenly sampled data. And if you don't get evenly sampled data, you run into some problems. And then the second part of the lecture will be about some of the problems that you get for computing the power spectrum over a limited epoch. If you do that, you cannot get the full real estimate of the power spectrum, and you need to do some, or you can actually take some measures to minimize that problem. And so that's the other thing we're going to talk about. So the first part is about unevenly sampled data sets, and the algorithm that is developed for that is called Lomb's algorithm, because Lomb developed it. It was developed by Lomb relatively recently, in 1976. Lomb actually was an astrophysicist in Australia, and interestingly, of course, these people are usually having data sets depending on when you can look at the stars that may not always be evenly sampled, because if you have a couple of cloudy skies, then your recordings may not be as available as when you have clear skies. And Lomb basically developed an algorithm that deals with that. And you would say, well, why would we use that in neuroscience? Well, I'll give you an example. Let's, for instance, look at a series of events like a spike train. Or an ECG recording. Then what you have is a number of events that are quite unevenly distributed. And now you can you have something if you would say, well, I'm kind of interested in the function that this represents. You could say, well, this interval is short, so that's a high frequency. This interval is a little bit longer, so that's a lower frequency. This interval is about the same, that's about the same then, and this is even a lower frequency. And then here is my my function. And as you can see, that function consists of samples that are not evenly distributed. So in neuroscience, we do deal with unevenly sampled data. Now, so what could you do if you have data like that and you still would like to get an idea about what the frequency content is of that signal? Well, you have a couple of options. One option is relatively straightforward. You say, well, let's just do some interpolation. You could use interpolation, and then if the time series is not evenly sampled, we just interpolate, and then it becomes evenly sampled. What do you think might be the disadvantage of that? Yeah, you have no clue it's right, because you are now introducing frequencies that originate from your interpolation algorithm, not necessarily from the underlying physiology. Yeah, absolutely. Then the other thing you could do, if you have a lot of spikes, you could also say, well, I'm going to use bins. So let's kind of look, say, well, I'm going to make bins like this. And then in every bin, I'm just going to count what the number of spikes is in that bin. That's often done. And then, of course, since your bin have equal spacing, you have an equally spaced sampled signal. So you can bin your signal. What do you think is the disadvantage of that one? Mm-hmm.
You lose information.
Yeah, could you be more specific? You lose information, that's correct. But
Because if you bin and there are 2 spikes, then you count them as 1.
yeah, that's true. But if you think about even a little bit about the algorithm, the Fourier algorithm, what are you actually doing when you're binning?
It's a low-pass filter.
Yeah, it's a low-pass filter. You're basically reduce your sampling rate. So instead of sampling fast, you're now sampling basically every bin. So depending on the size of your bin, you're actually seriously reducing your sample rate. And if you reduce your sample rate, what consequence does that have for the Fourier transform? You're reducing your Nyquist frequency, which means that you are reducing the extent of your spectrum. Well, sometimes that may not be a big deal. If you're interested in low frequencies anyway, that may be okay. But yeah, all the disadvantages that we just discussed, you kind of lose data. You're counting multiple spikes now as basically as a number. You're basically now reducing your sampling rate. That's, of course, the disadvantage of binning. And then the third alternative is you use Lomb's algorithm, which we will discuss now. Now let's say that this is our signal xn, because it is sampled at times 1, 2, 3, 4, etc. at Tn. And this is in principle is 1 over the interval, or sometimes people in electrophysiology, if it's a spike train, will call that the instantaneous frequency. But this is basically telling you what the rate is over which this data is evolving. Now what Lomb is doing, it's saying, well, I have my series xn, and I'm going to approach that with some kind of a function p, just as we did with the Fourier transform. And in this case, p is going to be just as the Fourier transform, depending on the number of coefficients, depending on the frequency, and depending on the times of sampling. And the function is very simple, and it reminds you without any doubt of the Fourier transform. That's this function. And what's kind of different than with the Fourier transform, because you can see that the same thing is true as for the Fourier transform. You have a cosine and a sine expression, and you have a coefficient for the cosine and a coefficient for the sine. So that's the same thing. The thing that's different is that we are not going to do that in multiple steps of the base frequency. I'm just going to pick any frequency that I like. So f here is basically a continuous variable. And then I'm going to, basically try to fit such a function to my data. And let's say that for a given frequency, this is one of the examples of P. could say, well, this may not work that fantastically because, and we already know that from when we were talking about the Fourier transform, is that, yeah, I mean, you had a lot of things that you had to do with the Fourier transform to just get it right and to make sure that the cosine and the sine terms behaved decently, etc. So what do we do here? Well, in this case, we say, well, for this given frequency, not only am I going to present this frequency like this, but now I'm going to shift this thing around so that it is maximizing the fit. So in this case, I could maybe shift this point a little bit to the left, or I could, of course, also, if I keep shifting to the right, I will also come to the top there. So I'm going to shift this thing. And then I go to the next frequency, and I'm going to again write that thing, and again shift it until it is fit in the best possible manner. So it's a very different approach there as compared to the Fourier transform. So now what is the rationale behind that shifting? As a matter of fact, it starts out very similar to what we did with the Fourier series. We are going to simply define some kind of an error over the sampled time series. And I just want to minimize this error. So I mentioned already when we did the Fourier transform, okay, you're going to see this again and again and again. And again, here you see it, people are minimizing something. Sometimes you do maximize something. You will see an example of that in a minute. So if we minimize this, for instance, we minimized it with respect to A and B, because that's what we want to find in first instance. Now if we start to minimize that function with respect to A and B, and let's kind of just look at the one for A. We get this expression. My blackboard is not wide enough, so I'm going to continue on the next line. So what I do, if I minimize this function, I take the derivative with respect to A. That's what this thing says. Then basically I apply the chain rule, so that is 2 times that expression. This is the expression for P, and this is xn. And then I still have to do the derivative of this whole expression relative to A. Well, xn doesn't contain A, but P does, and basically that's cosine. So this is the derivative, and this is 2 times the expression. What's that?
I don't understand the dot, dot, dot.
It means that it continues on the next line.
Okay, but what like operation is it? Is that
It's multiplication.
Okay.
Yeah. If you say nothing, it's multiplication. Otherwise, you would say plus. And sometimes you will say, if people find it confusing, you can say a multiplication sign. Is that clear? So let's kind of look at this, and you can see that now if we simplify this, we can rewrite this result and in this case the dot 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 means 2 pi ftn. As you can see, I just got rid of the 2 here, and then I kind of worked out the different terms, and then this is what you get out of this result. Now you can see that there is a cos squared term. That's the first one that's associated with A. And then there is a cross term, cos and sine. And this is the whole clue. These cross terms, they are annoying. So what do? We just apply tau for each frequency until the cross term disappears. That's the whole idea. Lomb's whole idea, and it works as a charm. So what you do is, because if you do the derivative relative to b, you get a similar expression with sine squared and a cross term, and the same cross term. And so what you are doing is you replace Tn by Tn minus tau. And you do that for every frequency. And then the cross term vanishes. When you do that, when you then basically perform that algorithm, and we actually will see that in a minute on in a MATLAB example. When you do that, you get basically for every frequency, you get an A and a B and a tau. And the best fit, and then basically at the end, and that's the whole idea, we then compute our spectrum. Using this equation. And realize here that when we do the FFT approach, we always look over a whole period. So that's the reason we can suffice with determining A and B. Since this doesn't have to be a whole period, this can be whatever data you have available, you basically square this whole expression. So that's what the p squared says. If you're done writing, then download program 8_1. And that will show us an example that I selected to compare it with the standard Fourier approach. I don't know if you recall that, but in the few lectures ago I showed you an example where we had noise with 2 sine waves. And then we looked at the signal and we said, well, this signal basically looks like noise. But then we did the power spectrum, we computed the power spectrum, and lo and behold, we found nice 2 peaks of the sine waves that we had injected in that noise. And here I'm using the same example for demonstrating Lomb's algorithm, and that is program 8_1. You can download that from Chalk. So this is the program actually that I'm listing here. I'll go to the top. So here you have a line that creates a bunch of random timestamps, and I sort the timestamps so that they are in order. And then I define my frequency scale from 1 to 500. And here again I have my frequencies that I'm going to inject, 50 and 130 hertz. Here I create that artificial signal, and here I add a little bit of random noise to it. And the variance of this thing is something that I will use later to standardize or normalize my outcome. So now the real thing that's happening here, that's the algorithm that it's all about, is that for every frequency, see here I'm looping through the frequencies, and for every frequency I'm going to compute my delay, tau, to get me the best fit. And then once I do that, I plug that into the equation that adds up all the power, and then I normalize it by twice the variance, and then I plot my result. So for every frequency I get an A, I get a B, and I get a tau. And since I then know what my signal looks like, I can plot the power spectrum. And here you see again the same result as that we had previously with that program 7_1, where we had the same signal. That again we have across, if you look at the time domain, it looks basically very noisy. If you now apply Lomb's algorithm and you compute the power spectrum, you can see that the peaks are clearly present. And when you run it, it may look a little bit differently, because yeah, of course we do random timestamps, so based on what your computer happens to give you at random data, it may give you a little bit different result, but you will find the 2 peaks. And another thing that's interesting, and you may not appreciate that from looking at this this part here, is that in this case the data was not sampled evenly, because if you would go to your previous program, you would see that the samples were taken evenly, but here you can see these samples are close by, this is a little bit farther, then it's farther away, then it's a bit closer by. So this is clearly a time series that was sampled very unevenly, and in spite of that fact, Lomb's algorithm basically pulls out the right frequencies. So take-home message here is that whenever you have a neurophysiological data or clinical data where you say, well, I'm looking at events and I have no control about when that event is coming, but I still would like to understand what the frequency content is, then go for Lomb's algorithm. That's the cleanest, and you won't have to deal with interpolations and binning in that case. I see a lot of people still binning their data when they do spike trains, and I think you get better and cleaner data if you do it like this. Is this clear so far? Because then we're going to step to the next algorithm. The next part is about the so-called multi-taper power spectrum estimate. It's a mouthful, isn't it? Multi-taper power spectrum, I will abbreviate that, estimate. You can say, and by the way, this was also a fairly recent addition to our toolbox. It was first presented by Thomson in 1982. And you would say, well, what is actually the reason or the rationale for this thing is if you have, and we already did that, if you have a discrete estimate of the power spectrum, we get something that looks like this. And I'm actually using the same notation as much as possible used by Thomson, so that if you decide to go into that paper, you can actually read it a little more easy. But this is the power spectrum. That is the notation that he uses for power spectrum. And the hat here, it means that it's the estimate. And we actually already know that, isn't it? We used a little bit different notation, but it is this summation over your time series multiplied by we basically rewrote that thing as the twiddle factor and things like that, but that's basically what that is. I left again a little open space there, but I did it on purpose. Because what are the problems that we encounter with the standard discrete estimate of the power spectrum? There are two actually pretty annoying problems. One of them is if you have frequency versus power, and in this case P is power, not a polynomial like it was over there. P is just power. And you get something like that. The problem is that you get a little bit of bias because frequencies leak away from larger peaks. So that's kind of an imperfection, and I'll explain to you in a little bit why that happens. And the other thing, so this is called leakage. And the other thing is that when you determine these power spectra, and we have seen that already a little bit when we did some estimations using the standard Fourier transform, these spectra are quite noisy. They're very rarely smooth like this. And usually when you see a smooth spectrum, somebody did some smoothing, because the raw spectrum basically is noisy by nature. Now the solution to this problem is to apply a window or a taper. That's the same thing. And that is something I'm going to explain in a minute. And to reduce the noise, you may have an idea what I could do to reduce noise here.
Do it many times and average.
Yep, you could average. Yep. And you could average in a couple of ways. You could, for instance, say, well, instead of looking at these points separately, I'm going to define small bands. So I'm going to reduce my resolution of my spectrum, and I'm going to smooth or average over these points within a frequency band. The other thing you could do is, if you have a time series that's long enough, you could put your time series in different epochs, compute the power spectrum of every epoch, and then make an average of these power spectra. That's another way you could deal with it. And as you will see, Thomson's multi-taper approach is using this, it's using that, and it's also using different estimates to average. So it's using basically all possible ways of dealing with these two kind of major problems, namely leakage and noisiness. Now let me explain the leakage first. I give a little bit of an artificial example to get the point. Let's say that we have this signal, a pure sine wave signal, and well, I'm not going to draw the whole thing, but yeah, imagine that it goes all that way and all that way. So what is the Fourier transform of this sine wave? Say it again.
It's amplitude?
Yeah, it's amplitude, exactly, at the frequency. So if I had the Fourier transform of this thing, I would have here a frequency axis, and here I would have some kind of an amplitude, or an amplitude squared if it was a power spectrum. The problem is when we do a discrete computation of the spectrum, we are not doing that. We're doing this. We have a finite piece of data. So instead of going from all the way there to all the way there, I am actually doing this. See? And I'm only considering from here to there. So when I do my discrete analysis, and let's say that this is the 0 line, then this is what I'm actually computing. Whoop. And let's again say that this is the 0 line. I've drawn this a little bit better. So you're just taking a little piece of that signal, you kind of cut a piece of that signal that goes from -infinity to infinity. And that's the one that you are using as the basis for your algorithm here. That's the xt that you are, or the part of xt that you are looking at. And now is the reason here that I left that open space, is that actually what I'm doing here is that I am multiplying this thing with some kind of a window, in this case a rectangular window, because that's really the signal that I'm looking at here, isn't it? And there is a somewhat nasty consequence for that. The nasty consequence is that if I look at the Fourier transform of this rectangular window, it looks a little bit like this. And here is frequency again. And here is power or amplitude again, depending on you're looking at power or amplitude. Now something that I still need to explain to you, and I will do that in probably next week, but if not the week thereafter, is that when you multiply in the time domain, multiplication, that actually translates into, in the frequency domain, in what we call convolution. And again, don't worry, we're going to kind of go into the depth of what convolution is in a couple of lectures. But for now, it basically suffices to say that if you want to convolve, because these guys are multiplied, so in order to get the result of this yellow signal, I have to convolve the effect of this one with that one. And that will give me the result of this yellow trace. And the convolution is actually, in this case, pretty simple. I'm just going to move this arrow over this signal, over frequency. That's the convolution operation. And so that means that instead of going to find this result, I'm actually going to find this result. Because when I move this thing over this structure here, I'm going to basically get this thing back. So that's a bit annoying, because not only do I get a peak where I expect it, you could say, well, okay, this is the peak is a bit broader than I would like, but at least it's at the right location. The problem is that you will also get energy escaping to the lower and higher frequencies due to these what is called side lobes. And so these side lobes basically cause leakage. And so because not only that thing will do it, but every frequency in your power spectrum will do that. And so every frequency will leak out. And for instance, we just did an extensive study to a high gamma rhythm in EEG. You have to be very careful then, because EEG contains a lot of delta rhythm, and the delta rhythm has a tendency to leak into the higher frequencies. So if you don't pay attention, you may actually get very biased values for your higher frequencies because of all the leakage that occurs from the lower frequencies that have such high amplitudes. So this is the problem. And you would say, well, why don't you come up with a window that has an ideal shape in the frequency domain? Well, that's a bit difficult. So the best thing you can hope for is that you have a window in the frequency domain that I would say looks like this. It has a little bit of a width, but not too much side lobes, or the side lobes are very low in energy. This is the best you can actually hope for. So now we come to the point of the multi-taper analysis. We are going to define a variable lambda, and lambda is going to be a function of n and w, and n is the number of points in your time series, which means your spectral resolution. And W is the bandwidth that you are selecting. So in this case, if I have my window here, the width of that window would be from minus W to plus W. So what is lambda? Lambda is nothing else than the following. I'll write it up first and then I'll explain it to you. What we are looking for is a window A with a Fourier transform capital A, such that when I look at a bandwidth, that the sum of all these things in the frequency domain within my bandwidth from minus W to W, that ratio relative to the whole energy from minus 1/2 to 1/2, which in this case means the Nyquist frequency, and because we set in this case we set sample rate to unity, so then your Nyquist frequency becomes 1/2, is basically reflected in this variable lambda. So what will lambda be if I have a terrible window? Well, if I have a terrible window, this is the total energy, then the amount of energy in my window of interest will be low. And if my window is great, then basically this thing will almost be the same as that thing, because almost all my energy will be in my window. So the way to say this is that we are going to minimize leakage by maximizing lambda. And we can do that by setting the partial derivative to 0. In this case, you're going to find a maximum. Of course, you have to, in this case, if you want to be really checking things out correctly, you should also look at the second derivative to see whether you deal with a maximum or a minimum. But in this case, I can assure you, you'll get a maximum. Well, if you do a bit of algebra, etc., you will see that in the handout. I give it to you step by step, and if you really want to follow it step by step, there is also an appendix that shows you what steps to take. But to make a long story short, if you do this, you get your window that looks the least possible way like this, where you have a lot of leakage, and the most possible way like that, where you have no leakage. And if you do that, you get an interesting equation, namely this. And this is your window, and this is your lambda. That will be the end result of your assumption. And D is a matrix that depends on a number of parameters. You can actually see that in the handout. It's just a question of following the algebra. Now this is an equation that a lot of people have seen probably, because if you realize that D is a matrix, A is a vector, and lambda is a number, what is this? What's that? Yeah, kind of a characteristic. You basically say, well, here we can determine the eigenvalue and the eigenvectors. It's a very well known equation in linear algebra. And so these guys are my windows or tapers that help me to approximate my ideal window as much as possible. There is actually one more thing that's interesting, is that what you get here, because the D is a symmetric matrix, so you basically get, according to the rule of linear algebra, you get a bunch of orthogonal vectors out of this equation. And that's something, for instance, that principal component analysis is using, PCA. They basically decompose the covariance matrix, which is also symmetric. So you could say that in a way these tapers are your principal components of your ideal window. And the nice thing is they are orthogonal, i.e. uncorrelated. So now let's say that I get k tapers. Then I can, for each taper, I can estimate my spectrum by multiplying my time series with that particular taper, and then do the spectral analysis and compute my spectrum. And then you average over these k tapers to get your estimated spectrum. Now let's quickly recapitulate what I said in the beginning. I said in the beginning of this topic that there were two problems. One of them was leakage, and the other one was noisiness. The noisiness you could address with averaging, and the averaging you could do over the frequency band or over a number of estimates. And I kind of predicted that Thomson would do everything. And here you see that indeed he does everything, because he tries to reduce leakage by creating a window that is as ideal as possible. Then within that window, because there is a bandwidth, it's not a single point in your spectrum, you're doing averaging because your window has a certain width. And then you get independent tapers resulting in independent estimates, and then you also average over these estimates. So this is a great way of basically reducing your leakage and also reducing your noise in the spectrum. If you now download program 8_3 from Chalk, we can actually look at an example. And I should say that what I'm doing here is something that I need to explain a little bit further in the near future, which is I'm using an autoregressive method, and that actually allows me to create or to compute the expected theoretical spectrum. So then I know basically what it should be. And then I apply to that time series the standard Fourier transform and the Thompson approach with the multi-taper. And the only way that you can actually get a reasonable idea of what's going on is if you run this a couple of times. So let's do that. So what you see here is one instantiation. Yours may look very different, but what you see here in black is my theoretical spectrum. And again, I can compute that from my autoregressive function. And I'll teach you how to do that in a couple of lectures. That's not the important point here. The point here is that if I take that time series and I use standard power spectrum analysis, I get here this blue line. And again, in your case, it may look different. You have to run it a few times to get an appreciation for that. And as you can see, here is an almost ideal demonstration that I get a lot of bias, a lot of leakage here from the low frequencies to the high frequencies. And then subsequently in red is the approach done by the multi-taper analysis. Of course, since we are using a random component in this time series, yeah, it may look a little bit different every time that you run it. So if you run it a couple of times, you will see that sometimes this thing is actually not too bad. It's similar, and in other cases, this thing will be just slightly above that one. And in some cases, it's like here that it's really terrible, and that it's there is a lot of leakage. And that all depends a little bit on the instantiation because of the random factor. I'll run it again for that case. Maybe it will look very different now. See? In this case, you would say, oh, there's not much difference here. And that's because I have a very different random set. Let's run it one more time. And here again, it's not so good, and my multi-taper approach is much better. So, take-home message here is that when you have to do a spectral analysis, power spectrum, it's probably a better idea to use the multi-taper approach. And the good news is you don't have to really program it even, because it's a standard function in MATLAB nowadays. But at least you now understand what's happening under the hood and what is the underlying rationale. If you go actually into the program here, you can see that command here. So this is the standard MATLAB command here. Let me see. I thought I had it here. Oh yeah. Somehow I had a hard time seeing it on the screen. Here is the command. So, and here is basically a standard MATLAB command that gives you the result based on the spectrum, or on the multi-taper spectrum. And again, taper and window is the same thing. Huh? Brings me to your homework. If you go to the exercises, I'm reorganizing stuff, so you will have now a chapter 8 and a chapter 8 star. And so what I want you to do is 8 star 1, 8 star 2, and 8 star 4.